Let's learn how can we use the concept of momentum in solving the rocket problem. First of all, I should go over the momentum and Newton's second law of motion. Um, Before that, I can remind you something from the previous video. Here we have some kinematics concepts and quantities, and here I will put some dynamics quantities. In kinematics, we have velocity, we have acceleration, and acceleration is delta v over delta t. I mean average acceleration. There are some big brothers for these kinematical quantities. Let's multiply the little brothers. Little brothers are the ones on the left side here in kinematics column by mass. So I multiply velocity by mass and I will get momentum. Momentum is mass times velocity, it's the big brother. Then the little brother of acceleration is multiplied by mass and I will get force, the big brother of acceleration, ma. And here, likewise, if I multiply both sides by mass, I will get force is equal to delta p over delta t. The same relationship that the big brothers have. It's very similar to little brothers. Acceleration and v have this relationship, and force and p also have the same, delta p over delta t. This is something we have already explained in the previous video, but let's start by F equals delta P over delta T. You know how can we accept this relationship. Now I can substitute the momentum. Momentum is mass times velocity. So let's import it inside the delta. So it's delta mv over delta T. Now, mathematically, I cannot always consider mass as a constant. So I will consider them separately. So let's say it is first time mass is constant, so it's mass times delta v over delta t. The second time, let's say velocity is constant and it's going to be delta m over delta t. So two different types of this delta mv over delta t are gonna be added up here. And what do we have? Here I have m delta v over delta t considering constant mass, and the next time v delta m over delta t considering constant speed. Okay, so what's the benefit of this relationship? Actually, you may remember when I introduced Newton's second law, F was introduced as F equals ma. You remember, and it's exactly F equals ma, the first term. So if I just disregard this one and consider the first term, I can go back to the Newton's second law. It's very easy to understand. You know everything about it. But the problem is that here, unfortunately, I have an extra term. What should we do with that? I will exactly go over this relation, which is very useful in solving the rocket problem. Before I go over that, let's say we have a system with constant mass. If the mass is constant, actually delta m will be 0. Constant mass means no change in mass. So if delta m is 0, we don't have the second term. Like the car problem. Suppose that there is a truck here and the truck has almost the same mass. When I say almost, it's not a considerable change. You know, mass of the truck is not actually constant. When it's consuming fuel, it's losing mass, but it's very small, so negligible. So let's say the mass of the truck is constant. Mass is constant. If the mass is constant, I can say the engine force, which is pushing the system forward, let's say is F, can accelerate the truck. Let's say this force is 4,000 Newton. And the mass of this truck is a small truck. Let's take the mass of the truck to be 8,000. Oh, it's not that small. Let's say it's 2,000 kilograms. Okay, so here I can say F is equal to m delta v over delta t, or same as acceleration. Force is 4,000 Newton is equal to 2,000 mass times acceleration. So acceleration seems to be 2 meters per second square. This is something very familiar for you, and in dynamics we have already learned it. This is not our topic of discussion today. We should go over the second term, this one. What should I do with this one? V delta m over delta t. So let me start from the scratch. Consider a rocket in a space. When I say rocket in a space, means that there is no gravity, there is no air resistance, nothing. Actually, it's in isolated space. So the total net force acting on this rocket is considered to be 0. Okay, let's say the astronaut turns on the engine and the rocket starts moving. Normally, when the rocket goes to the right, it should push the gas out to the left side, and then gas is going to left, the rocket goes to the right. This is something we see. Okay, the more you wait, the more the gas is pushed out, and so the more the acceleration or the more the displacement of the rocket. More time, more gas pushed out, and more displacement in rocket. But you should know that always the rocket plus the total mass pushed out, the total gas pushed out, are in this box, or this box, or this box, or this box. These boxes are going to be extended in a space, but the center of all boxes are almost at the same place. So the center of the system is not moving. Although the rocket is accelerating rightward, but of course the gas is also pushed leftward. So totally there is no displacement in the system. The gas is displaced leftward, the rocket is displaced rightward, but the total system is at rest, is still at rest. Why? Because the net force acting on the rocket is 0. As the rocket at the beginning was supposed to have no initial speed, still it should remain still. Actually, it should remain at rest without any net displacement of the center of mass of the system. This is the problem of the rocket. Now let's consider the aforementioned equation in this case. I can hold it here just to remind you what I explained about the rocket. Confirming the total net force acting on the rocket is 0, and then I substitute that by m delta v over delta t plus v delta m over delta t, which is going to be 0. You know why. Okay, let me tell you something. Here, actually, when I mention mass, is the mass of the rocket, not mass of the system. Be very careful. Mass of the system is mass of the rocket plus the gas, the pushed out gas. But I don't consider that. It's just the mass of the rocket. Delta V over delta T is the acceleration of the rocket. V is the speed of the gas pushed out relative to the rocket. The speed of gas. And delta M over delta T is the rate of change of mass. Let's say in each second, a mass of, 4 kilogram is pushed out. So delta M over delta T will be 4 kilogram per second. This is rate of change of mass. In each second, actually, the rocket will lose 4 kilogram of mass. The system in total will have the same mass, but the rocket is losing mass. Be very careful. From system, I mean rocket plus the gas. When I say the rocket accelerates, I do not mean the system accelerates. Okay, what should I do next? It's very easy. Actually, I can take the second term to the right, and it's a negative sign you see here, showing the direction, and I can substitute delta V over delta T for acceleration. So it's let me write it like this: m times acceleration is negative V delta M over delta T, and then you can take the mass here. So I can write it like acceleration is equal to negative V delta M over M delta T. Again, this is the mass of the rocket, delta m over delta t, rate of change of mass. The rate of the change of mass is actually the total mass in each second that it's pushed out from the exhaust. And the v is the relative speed of the gas to the rocket, and acceleration of the rocket again is here. Be very careful. Now let's consider a problem and solve it and then learn it deeply. A small firework rocket has a mass of 65 grams. So let's say there is a small firework rocket. The mass of that is 65 grams. The initial rate at which hot gas is lost from the firework has been lit is 3.5 grams per second. And the speed of the release of this gas from the rear of the rocket is 130 meters per second. What does it mean? Here I have a delta m over delta t, which is given to be 3.5 grams per second. Later I will convert it to SI units. And the speed of the gas pushed out is 130 meters per second. These are the available data. Calculate the initial acceleration of the rocket. Why they say initial acceleration of the rocket? I can show you something. This is the initial rate. Okay, the rate of the gas, because of the technical problems or complications, whatever, may change. So the initial acceleration of the rocket is based on the initial rate of the gas and initial mass of the rocket. Because there is still a very important problem. We have the initial mass of the rocket 65, but as the rocket is losing mass, the total mass of the rocket also will change. So we can just calculate the initial acceleration. Let's do it like that. Acceleration is negative v over m times delta m over delta t. We have everything almost. So let me write it like this. And as we are looking for the magnitude of the acceleration, I ignore the negative sign. Here the v is going to be 130 meters per second. So let me put it here. Mass is the mass of the rocket. At the beginning, the initial mass is 65, but it's going to be 65 10 to negative 3 kilogram in SI units. And the delta m over delta t is 3.5 gram per second. I will convert the gram to kilogram, so it's 10 to negative 3 kilogram per second. Now everything is in SI units. So let's do it like that. And then I will find 7 meters per second square. This is the acceleration. Just be careful here. I should attract your attention. It's 65 times 10 to negative 3 is also 10 to negative 3. And then I've already dropped this. 7 meters per second square is the acceleration of the rocket. Of course, the initial acceleration of the rocket. I can remind you something. Acceleration is negative v over m delta m over delta t. Let's say we invented a specific rocket which has a constant rate of change of mass. So the rate of change of mass is delta m over delta t is constant. Technically, they can keep it constant. Here, the problem is even if I push the mass, the gas out of the exhaust at a constant speed and adjust it, I cannot keep the total mass of the rocket constant. So necessarily the mass will change and will be less and less and less. So acceleration of the rocket will be more and more and more. So if I draw the graph, the acceleration of the rocket technically cannot be constant. It will increase, increase, and increase. And then finally, it will go to the zero. What do I mean by that? Let's say the acceleration increases to a maximum, and then after that, it may be like that. And then the acceleration at the point when you lose all the gas, there is no fuel anymore, lost fuel, total fuel is lost, the acceleration immediately drops to zero and continues with no acceleration. So the acceleration will increase, but finally it will drop to zero. This is something I should remind you as a technical problem. Of course, considering the instantaneous acceleration in rocket needs more calculus, and it's not a topic of discussion now in this video. Thank you for watching this video. I hope you learned it. Please take note and practice. See you.